Alrighty, welcome back from reading week. Where the hell did everyone go? All right, yeah, I guess I released the test one back, so everyone dropped it. So everyone here did well, yeah. You should be able to see the average on CrowdMark. So I think the average is like 71, but a good handful of people like blatantly failed. That is bringing down the average quite a bit. I usually check to see who did really well, and I've not seen their faces before, so I assume that's why. And all the faces I recognize did good, so. All right, so welcome back. Where'd we end up? We ended off before reading week talking about threads. So you are going to be in for a treat. So tonight your lab, whatever is due, also could be the reason why no one's here. So this is your primer for the next lab where you are going to get the opportunity to write your own threading library. So just as a review, where we were leaving off before reading week, we were talking about processes with threads. So to draw everything kind of visually all together, we have this abstraction called a process, which abstracts or is supposed to represent a running program. So some things in your process, they're going to be a list of open file descriptors, all the file descriptors that process is using. Then, of course, it's going to use our good friend virtual memory. Virtual memory, that's where all of the memory that this program uses is. And global variables will be in virtual memory. The compiler just picks a random address, and the operating system has to figure out how to map it. You now know it would just have to figure out which page table entry it needs for the mapping to be valid, set up the permissions, all that stuff. Then the heap would also exist in virtual memory. There's a system call to grow the heap. And then we can have threads that also live within a process. So the only thing that are independent on threads are their registers and their stacks. So their stacks also live in virtual memory, but they should be independent because, well, each thread needs a stack to execute, run functions, and things like that. And we saw before the break what happens if you give the address of your stack to a different thread. Bad things happen, and you should not do that. So for the most part, each thread should have its own independent stack, its own set of registers. And guess what? For the next lab, you're implementing user threads, so you're going to have to keep track of the registers and keep track of the stack and do some scheduling. The purpose of this part of the lecture is that I'm going to show you how to deal with all the register things, how to deal with the stack things, how to allocate a stack. I've written that for you. How to swap the registers. Previously, the old version of this lab, you had to manually swap the registers, so you had to look at like x86 documentation, which is why that lab took like 80 hours. I'm nice, and I'm going to show you how to do it without having to read x86 documentation, and as a plus, your implementation will work on ARM and x86. So joy. So any questions or any reminders I need to give people before we start diving into it? All right, cool. So remember, you can access these examples. There's that materials repository. Look specifically in that directory. And you can find all this code there. You may or may not want to do some copy pasta to actually help you and implement it in your code. So actually, let's do the second thing first. So far, you've probably had to implement your own linked list, right? That is a thing for suckers. I highly suggest you do not implement your own list. So you're free to implement your own list, but remember, you're going to have to keep track of, a queue of threads and schedule them in FIFO order. So that tells you that, hey, you probably need a linked list. It's probably the easiest thing. If I'm doing round robin, right, I'm scheduling the thing at the front of the list. Whenever I reschedule something, I throw it to the back of the list. So I probably want a doubly linked list. Again, you can implement if you want. I highly suggest you don't, because that is a lot of debugging you might have to do. If you don't want to implement your own, there is this sysq.h, which is a way to have it write the implementation for you. So it defines a whole bunch of macros. It's kind of ugly to use, but as soon as you do have it, you can change the type of the list if you really want. Much easier than having to, if you wanted to go from a doubly linked list to a singly linked list, you'd have to change all your functions, remove the previous pointer, blah, 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 blah. For this, all you do is, so tailq is what a doubly linked list is called. A singly linked list they call slist. So if you wanted to change this from a doubly linked list to a singly linked list, you just replace tailq by slist and you're done. You probably want a tailq, so you want a doubly linked list. And what you probably will have is a queue of a whole bunch of threads you want to run. In this case, how you use this is you define a struct saying what your list element is, and you can list, it's a normal C struct. You can have as many fields as you want. Probably, if you want to keep it minimal and you just have a run queue of threads, you probably just have one int, which is an ID, which is a thread ID of what thread to schedule. So this is actually a list you could actually use. And then if you were to implement your own linked list, you'd have to do like next pointers and previous pointers and stuff like that. How this library works is you use this tailq entry macro, and you give it the name of the struct as an argument, and then just something to call the pointers. And whenever I use it, I just call it pointers all the time. So this will just create any pointers you need for this linked list, and it will refer to it as the name pointers, which is something we'll have to use in the other macros. So this essentially defines the next and the previous for you. And then in order to make the list structure itself, which is just pointing to the head and the tail of the list, the macro is tailqhead. So this is what you want to call the struct as the first argument. So I just call it list head because I'm not creative. And then you give it what the struct name is of each individual entry. So in this case, I just called it list entry. And then after this macro, it defines a struct called list head that represents that list for you. So in this case, and probably in your case, you're going to just have one linked list of all of the threads to schedule. So I can just do like static struct list head and call it something creative like list head. So this will create one list for me. Then if I want to use this, iterating over it is again a macro, but it's a bit nicer. So if I want to iterate over every single thing in the list, well, I just create a pointer to a list entry, call it E. I don't have to initialize it or anything like that. Then I do this tailq for each macro. So it will update this E to point to each individual element one by one of the list. And you have to give it the pointer to that list head. So I give it the pointer to my global variable there. And then you also, as the last argument, have to give it the name of that pointer thing. So in my case, it was just pointers. And then now it's just iterating over each individual element of the list. So if I do dereference ID, that will give me the ID of everything that is currently in the list. Questions about that? Yeah.
So does this imply that each list entry can have multiple pointers because but we're only using like one?
Like, does it imply that there's no circular things or anything like that?
Because in the list entry struct, the second element is, you named it pointers with an S.
Yeah.
So does this mean that there could be like multiple?
Yeah, I named it pointers with an S because it could have multiple pointers, in which case it will. If it's a doubly linked list, it has a previous and a next, right? That's why I always just call it pointers, because maybe one, maybe multiple pointers, depending on what it is. I just call it pointers all the time. All right, so that's that. Any other questions with this? All right, so if I want to access the last element of the list, I can do tailq last. So maybe I want to see what is at the end of the list. If you want to see what the front of the list, you can just go ahead, look at the man pages or Google it or whatever. There's a whole bunch of tail Q macros. There's like tail Q last, tail Q first if you want to get the first element. So this would give you the last element and point to it. So it returns a pointer to that list entry. And then I can go through and see whatever the last element is. Again, dereference the ID, because that's the only thing I care about. Then in main, how I actually initialize it is I use tail Q init. I give it the address of my global variable. It's C. Of course, you have to do everything through pointers. And then, well, if I just created the list, it should be empty. So there's this assert tail Q empty, just returns whether or not this list is empty. Well, if I just initialize it, it shouldn't have anything in it. So it should be empty. And then here, unlike your code, if I declare struct list entry E1, E1 lives on the stack, so it only lives as long as main exists. You're writing a library, so you don't want to do this because, well, if your function returns, then that variable no longer exists and you're pointing to invalid memory and bad things happen. So you're probably going to need to malloc it in your program. For demonstration purposes, I just do create it on the stack. So I create an entry called E1, set its ID equal to 1, and then I could do insert tail. So this is probably what you're going to do if you're doing round robin, right? You're inserting it at the last element, so that's called insert tail. So I give it the address of the list to add it to, the address of the entry, and then the name of that pointer thing, which is in the struct above it. Again, I always call it pointers. So I can printf inserted 1, print list. In this case, it should just print 1, right? Then I create another entry, inserted in the tail, so inserted at the end. So in order, it should be 1, 2. Print off that I inserted 1, print the list, so it should be 1, 2. Then print the last element of the list, which of course should be 2. I just added it. And then there's this tail Q remove, so you can just remove any single element you want. So in this case, it has to be in the list. So in this case, give it the list to modify, the pointer to the element you want to remove, and then the name of the pointers again, so then it removes the element 1. So if I print list, only the element 2 should be in the list. So if I go ahead, compile this, run this, tail Q, I can see that it indeed works. I insert 1, I see 1 in the list, insert 2, the list has 1, 2, the last element is 2, remove 1, now the list just has a single element in it. Questions about the linked list? So again, I can't tell you what to do. Highly suggest doing this because this linked list works, and debugging a linked list on top of debugging the rest of it is going to be no bueno. So that was Spanish. I'm multilingual. Actually, no, I'm not. I can barely speak English, but I know C. So any questions about the linked list thing? Everyone's going to use this, right? Not implement their own linked list? Perfect. All right, so now the harder question, or harder part. So this is basically kind of very similar to the skeleton code you will get. So I provide functions where it just allocates a new stack for you. So it uses mmap. You do not have to read this. You just have to use this new stack function whenever you create a new thread. Then that new thread needs a new stack. So you use this function. It just returns a pointer to you. Don't worry about the arguments. And you want to use this. So some things it does. So if you do not use this function and use Valgrind, if it's running a user thread, Valgrind really freaks out when it's not using the operating system allocated stack, and it really, really, really freaks out. So in order to make Valgrind happy, you have to register the stack with Valgrind. So this also does that. So you can actually use Valgrind to debug your code, which you are going to want to do. And then I have this delete stack function for you. So it just takes as an argument the stack pointer it got returned from a new stack call, and it deletes that stack for you. So you should go ahead and clean it up. All right, the first new thing is going to be this uContext type. So this uContext type abstracts all of the registers and everything for you. So that's what this is. So with that stack function and this uContext type, that is basically a user thread. That's like the core components of it. So getting a stack, well, you just new stack, delete stack, and then I'll show you how to go ahead and have one of these uContext things use that newly allocated stack, and how to use them to save the registers and restore the registers. So this will do all the heavy lifting for you. So every time you have a uContext, I highly recommend, I don't know how you would do it otherwise, you should have a uContext for each individual thread, because this will save the register. This is the location to save the registers to and restore the registers from. So in this little example I'm going to show you, I'm going to have 3 threads. I'm going to have thread 0, thread 1, and thread 0, thread 1, and thread 2. So they each have this uContext type. Then here, oh yeah?
Should you also have a T0 stack, or were you going to get to that?
Yeah, so the next question is, shouldn't I have a T0 stack, or am I going to get to that? So in this case, I need a stack for thread 1 and thread 2. And I'm going to consider thread 0 as being special and the main thread. So the main thread that starts executing main has to have a stack, right? So it has to have a stack. So whatever stack main gets, we're going to call that thread 0, and that's going to be our special first thread. So we don't need a T0 stack because we're going to just use main's stack for it. So does that answer that? All right, perfect. So let's skip all this. So how it works is whenever, there's 2 things to do with this context type. There's either saving to it and restoring to it. So the saving part of it, it's not called save context, it's called get context. So I have this has all sorts of comments in it too if you use this later. So get context will save the current state of whatever thread is executing this, save all of its registers to this uContext type, such that it could restore it and start executing again from wherever it left off. So if I restore it, it would actually fudge the program counter a little bit, that if I restore it, T0 gets restored here now. And you get restored to wherever the last place you saved. So it's kind of like a checkpoint. So if I were to restore T0's context, it would resume right after this get context call. So first bug you will encounter that will hurt a little bit is if I do set context. So set context is restoring context or going back to the previous saved registers. So in this case, if I set context, it goes back to the last place I saved them. So in this case, it will take whatever the current thread executing's registers currently is and restore them to match whatever was saved in this uContext type. And it's C, so it's always passed by pointer. So in this case, if I do set context here, what's going to happen? People are doing this, right? So this will be your first encounter because you can infinite loop without trying very hard. So in this case, if I did printf, so if I compile and run this, I will go ahead and see that, hey, I infinite looped myself. So this is going to be the first fun thing you do, because what I did, I saved the current executing threads, all of its registers and everything to this thread 0 uContext type, such that if we restore it, it would get restored right after that. Looked like it would get restored right after that call to get context. So this doesn't change anything, it just saves it to that structure. So it would print F, and then set context would restore it. So it would jump back here, kind of rewind, restore here, print F, and then set context, come here, print F, set context, get X, infinite loop itself. So questions about that infinite loop? Probably first fun thing you will probably encounter. Hopefully you don't encounter it now. All right, one infinite loop out of the way. So we want to do something. So in order to make a new user thread, well, let's go ahead and go through all the steps with that. So what you're going to have to do is, well, let's create thread 1. Thread 1 needs a new stack, so I call that new stack function. It goes ahead, gives me a pointer back to a new stack, and registers it with Valgrind, all that stuff. So if I want to create a new context, I always have to get context to initialize this uContext structure, even though I'm going to quickly make a function call that reinitializes everything. But the rule is you always have to initialize it by using getContext, even though I don't want to restore the current main thread to be saved into that uContext thing, but that's just the rules. So I initialize it using getContext, that thread 1 uContext, and then there's some things I can do because, well, to create this new thread, like pthreads, you tell it what function to run, and well, there's a stack pointer register, so we have to register our stack with it such that it will change that register to go ahead and use our stack. So to do that, I do t1 uContext, and there is this uc_stack type where you have to change two things. So you have to change ss_sp, so the stack pointer, to point to t1 stack, and then set the size of the stack, which is just going to be this given default stack size. So just always use this. So this will set the size of the stack and the stack pointer, and then you don't have to worry about it. Then what we're going to do is to initialize, that will take care of setting the stack pointer, and then to take care of initializing the program counter such that it will go ahead and execute a function. We have to use this make context. So for make context, first argument, we give it a pointer to the context to modify. Again, that has to be initialized with getContext. Then as the first argument, you have to give it which function it will run. So it will change the program counter such that if we do a set context to it, we will start running this function instead of whatever was currently saved. So unlike pthreads, by default, the function you give it accepts no arguments and returns no arguments. So it's void void. But you can actually pass it multiple integer values if you want. So it has variadic arguments. They all have to be integers. But here you can specify how many ints you want to pass it by using this argc. Of course, you can set it to 0 if you want. And then you have to pass it all of the values you want it to set. And again, you can only pass ints. So in this case, we pass it the number 42. So after we do make context, it just saves, just messes with the registers for that t1 uContext type, such that if we set context to it, it will go ahead and start running this t1 run function and use t1 stack. So any questions about that? All right, so let's see what this t1 run. So t1 run, just void, so it doesn't return anything, and it has one integer argument just to see that we get, or show that we can actually pass it. So it should get the value 42. So we can go ahead and see if we can use it. So let's give it some space here. So if I want to simulate, swapping from thread 0 to thread 1, what I can do is I can do something like this. So I can do set context, and then set context to t1's uContext. So if I do this, that will modify the current registers on the CPU, restore them from this uContext structure, which I just initialized. So it should set up so that this t1 uContext is using t1 stack, and it's set up to run this t1 run function. So if I set context to it, then what should immediately happen is it changes the stack that's being used, and the program counter, such that we start running this T1 function. So if we run this now, it should say, hooray, got arg42, and then we finish T1 run function. So if this was pthread, that would implicitly call what? Pthread exit, right? And then that would just end that thread, and then it would probably resume from the main thread if this was pthreads, right? Well, turns out it doesn't work like that with uContext. So if we do this and we run it, we just see, hooray, got arg42, and we didn't continue executing the main thread. So what happens by default in this case is if a uContext makes it to the end of its function and returns from it, it just calls exit and ends the process. So for your code, since you're implementing user threads, you're going to have to handle this. So if some thread ends, well, your first task is going to be like the pthread library. If there's another thread to execute, switch to that thread and go ahead and execute that thread. So some ways I can actually do this is without spoiling anything and how you have to do it generically, I could just kind of hard code it. So I went ahead and, well, I still have thread 0 to run, right? So if I still have thread 0 to run, what I might do is before I exit thread 1 run, I could do set context to thread 0 uContext. So I can go back to that main thread, right? Is the idea behind this. So everyone think that that's a good idea to do. Let's pull this down a little bit. Okay, or not. So anyone think that's a good idea to do? Yeah. Yeah, that will restore it back to where you last did a get context, which was right here at the beginning of main, right? So if I do this, and I run this now, what do I expect to see? Probably a whole bunch of hoorays, right? This should infinite loop myself, but infinite loop myself worse, I guess. There's degrees of infinite loop. This one is worse. So if I run that, hooray, got arg42 over and over and over again. I should probably stop it before it crashes. So why this happens is because, well, I just infinite loop myself in more steps. So my program started running main, did a get context, so it saved all of the registers that were running this main function to thread 0 uContext. Then we went ahead, created a T1 stack, initialized T1's uContext, set up its stack pointer register, did a make context, so set up its program counter and all that, and then we did a set context to it. So that would change to here, use T1 stack, print hooray, we got this, then set context to T0. So that would get restored to the last place we actually went ahead and saved it, which would be here. So it would go back here, recreate a new stack for thread 1, overwrite stuff, come back, print it, blah, blah, blah. We infinite looped ourselves in more steps. So questions about that infinite loop? All right, second thing you might encounter. So your next question might be like, oh, okay, well, how do I actually resume? So let's make this a bit more interesting. So let's go ahead and set up another thread. So we'll call a new stack. We'll start initializing T2. So we'll get a new stack for T2, initialize its uContext with get context, mess around with its stack pointer to use that stack we just got, and then just do a make context. And here I just do the really short version where I just tell it to run thread 2 run, and I give it no arguments. So if I do a set context to it, now it should say T1 should be done, switch back to T0. So what I'm going to do here is change this to be, instead of set context to T2 or T0, I'll just set context to T2. So now, if I run this program, main should create thread 1, thread 2, then go ahead and run thread 1. So it would do hooray, got arg0, print 42, then set context before to thread 2. And in this case, it would start running T2 run using T2 stack. So in this case, for this little program, I'm kind of hard coding it. So I'll say T2 should be done, switch back to T0. So I know, just because, I don't know, I know that we're not going to come back to thread 1, so I can delete its stack. I can clean it up. I don't want to try deleting thread 1 stack from thread 1, because deleting your own stack while you're executing, which requires a stack, is a recipe for disaster. So don't do that. People do that all the time, and they wonder why they can't debug anything. So do not delete your own stack while it's being used. So this is also why, joining is the only thing that cleans up things, because you know that, hey, a different thread is cleaning up your stack. That's safe to do. So this thread cleans up T1 stack and then sets context back to T0. So if I execute this now, again, it will infinite loop itself in an additional step. So ideally, what we want to do is, well, we actually want to come back to wherever T0 left off. And this function was not, you were not allowed to use before, but I'm going to let you use it. So there's this swap context function. So the swap context function is very special. So what the swap context will do is it will do a get context on the first argument and fudge it a little bit, such that if I do a set context now on T0, T0 resumes here now. So it resumes here, right where it left off, and what context it will switch to is T1. So if I put that there, what will happen now is I will save the current context, so the main thread that is executing this, which we're just calling thread 0, save all of its registers to this T0U context, and then I do a set context to T1. So I would start executing this code with T1's stack, and I would say, hooray, got arg0, 42. Then I set context to T2, and then T2 runs. Then it says T2 should be done. Switch back to thread 0, so it deletes thread 1 stack. Then does a set context back to thread 0. So because I use that make, or that swap context, T0 returns here. Then it should print off main is back in town. Then the main thread delete threads 2 stack, and I've cleaned up everything all well and good. So let's compile, run that, make sure it works. So if I compile, run that, hey, it looks like I'm running thread 1, thread 2, resuming back to the main thread, joy. So questions about that fun thing? Yeah?
So it technically moves your get context to after the swap context?
Yeah, so swap context fudges because it's it'll get context this and set context this, and it'll fudge it a little bit such that T0 resumes here. Because without the swap context, you can see how you get into a little bit of a bind, right? So I'd have to do get context. If I want T0 to resume there, I have to do a get context, T0U context, and then I also want to set context to T1. Right, it's kind of what I want to do, but what's the problem with doing that? I'll probably, yeah. Yeah, when I set context T0 back, T0 resumes here, right? Which will immediately do a set context to T1 again, which is not what I want. So in the past, which is why this lab took like 80 hours before, but I'm way nicer, you were not allowed to use swap context. You had to figure out this little mystery without using a function they give you. So you go ahead, just do swap context. It will fudge it so that T0 will return after that swap context. You don't have to worry about saving it or doing anything like that. So questions about that? All right, so another thing you can do, another option you have is by default, if it makes it to the end of a thread's run function, it will just go ahead and terminate that process, which is not what you want to do as you are creating a threading library, as long as there's another thread to run. So you could fudge it so that it kind of like implicitly calls like thread exit and figure out which context to swap to. Or what you can do is kind of have like a little cleanup thread. And another option you can have is in this uContext type, whenever you're doing make context, there's this field called UCLink. So what UCLink will do is whenever this run function hits return and it returns from that run function, if a UCLink is set, instead of exiting the process, it will magically, well not magically, but it will always do a set context to whatever this link is. So in this case, if I set UCLink to T2 uContext, that means that if T1 run actually makes it to the end, it will automatically, well, it will implicitly do a set context to T2 uContext. So if I wanted to, I could just get rid of this set context now because I did UCLink. So now if T1 run makes it to the end, it will automatically do a set context to T2. So it should behave exactly like before, where it should print off T2 should be done, switch back to T0, delete T1 stack, set context, and all of that fun stuff. So if I run it, it should do the exact same thing, where it works pretty much the same way. So questions about that? Yeah?
So it's like, so the next thread that you decide to run is based on like your implementation of round robin?
Yeah, so in general, when you set, if you use UCLink, in general, right, when this thread runs and makes it to the end, at the time you do make context, you don't know what the next thread going to run is, right, whenever that thread dies. So when you do a UCLink, you probably want to do it to your own little cleanup thread that just has enough, you can make it your own internal threads if you want, and you can make a thread that will go ahead and clean up things for you if you want. So you can always UCLink to the same thing. It could go ahead, do the cleanup and all of that, or you can add logic to implicitly exit or do whatever you want. There's like 2 main ways to do it. So up to you. But yeah, in general, you don't want to UCLink to some thread that is a user thread that someone created because you don't know at the time you make context what thread will run after you die, right? Yeah? So your cleanup thread, so this skips a bunch of steps. So you're going to implement joining a thread, right? And when you join on a thread, you have to wait for it to terminate. And when it's terminated, then that thread can go ahead and clean up its stack, just like how a pthread library would work. And I think I released all the documentation early if you want to look at it during the break or whatever, but it should say basically what the responsibility for all the threads are. You're implementing join, exit, create, and yield, which basically just goes to the next thread. I think that's it. Oh, and cancel. So cancel is going to be your version of kill. So you're going to force a thread to die a fiery death. All right. Any other questions or anything like that? All right. So let's, oh, crap. Do I have this example? Shoot. Okay, so back in the past, when you could not use that swap context, let's see if I have it. When you could not use that swap context, you had to painfully, and I mean painfully, implement it yourself. So it was also used as a like midterm question. Let's see if I have it. I should have it somewhere. All right, let's take our break early while I find it. Yeah. Alrighty, so how you would implement swap context, I guess you're supposed to figure out from questions like this. So this question is like, hey, we have two uContext set up so that uContext A is set up to execute thread A, assuming with its own stack, and then we have another thread with purple. So we have another thread, thread B, set up to initialize its own stack. Its uContext is initialized to start executing this code. So we have a global variable called int I is currently equal to 0, and this is where it's going to be important what's allocated on the stack, what's allocated on the global variables, because anything allocated on the stack is going to be local to that thread. So at the bottom, this would be in memory, so I'll just draw out their stacks. So this would be T1's stack. Oops. Why is that getting deleted? What? Okay, whatever. And then T2 stack, and all its local variables would be on its stack. And the stack is in memory, so if we did any or set context or get context, that only changes the variable. It won't change anything in memory. So it's set up so that one kernel thread calls set context to UA. So we start executing the thread A function with thread A stack. So this is going to be like first year C. So we declare a variable called D, initialize it equal to 0. Where does the variable called D live? On thread 1 stack, right? So I would have a variable called D, and its current value is equal to 0. Then I go here, I have a while loop, so I check if I is less than 3. I is a global variable. What is its current value? 0, right? Is 0 less than 3? Hopefully. So we're going to go into here, I++. That should increase the value of I from 0 to 1, right? So I increases from 0 to 1 after that line. Then we print off A, and then printing off whatever the current value of I is, which should just be 1, right? So we would print off, let's see, what text color. So let's say we have our little console here. Oops. Stop it. So this would print off A is 1, right? So then it does D equals 0. What D am I changing? Thread 1's D. I'm changing D from 0 to 0. Don't have to write anything if I don't want. If it makes you feel good, you can erase a 0 and write a 0 again. I'm not going to do that. Now, originally, the get context was set up for UA such that it would resume right here, right? But now it does a get context call. So it's going to save all of the registers, including the stack pointer. So the stack pointer is going to be T1 SP. Stack pointer is going to point at the top of the stack, so it's going to point there. So it's going to save all of the registers into this UA function, such that UA, if we do a set context on it, it would get restored here, right? So everyone's still with me? All right, so now we check if D is equal to 0. Is D equal to 0? Sure is. Now it's going to change the value of D from a 0 to a 1. So it would change the value of D on thread 1 stack from a 0 to a 1. Then we do a set context to UB, right? So we'll jump over to thread B, start executing with thread B's stack. So let's follow this purple arrow. So it declares a variable called d equal to 1. Should I be modifying that thread's d? No, right? This would declare a new variable on thread 1 stack, also called d, and its initial value is equal to 1. All right, then next thing it'll do, so its uContext was saved such that UB, if we do a set context, it gets restored at the beginning because that's where it was last saved. So we get while I is less than 3, current value of I is 1 less than 3? Sure is, so it'll do plus plus or I plus plus. So it will change the value of I from a 1 to a 2. And then print off B and the current value of I. So this should print off B2, right? So next thing it'll do is it will set its value of D, right? This is B's D from 1 to 1. Again, I could erase the 1, put a 1 if I wanted to, but I'm not going to do that. Next thing it executes is a get context. So it saves everything in this UB struct such that it would resume here. So I'll just swap the arrows real quick. Now it'll check a D. Is D equal to 1? Yes. So it will set D equal to, oops. So it'll set D equal to 0. And then do a set context to UA. So it will come back at whatever A was set to. So now it will resume back here and then check what's its current value of D. Yeah.
Would it still be 0 because we just saved this whole step from get context?
So yeah, this is where it's important. Get context just saves the registers. So it just saves the registers, does not save the stack. The stack lives in memory, right? So what it would save is a stack pointer. This stack pointer hasn't moved. So this variable D still exists, still at the same part, and this is the only tricky part. So when we come back, well, the D value is whatever it was before. It doesn't restore whatever was saved in memory, right? It only restores the registers. So D is currently 1, not 0. So is D equal to 0 there? No, right? So now this is false. So it's going to skip over the set context. And this is basically the trick to implementing your own swap context, right? So first time through, it does the set context. Second time when it comes back, it skips over the set context. So you could use this to implement your own swap context if you really wanted to. It's basically using a flag to keep track if I came back or not. But this is in a loop, but for your own, again, just use swap context. But this is basically how swap context works. So this time I came back, D is 1, so this is false, so I skip over it. Check here, is I less than 3? Well, it's currently, value is currently 2, so that is currently true. So we do plus plus I. So I changes from 2 to 3. We would print off A 3. Then it would change its value of D on its stack from 1 to 0. Then we do a get context again, so it would save such that it resumes at the same place. In this case, it doesn't really do anything because it's already going to resume there. Then it will check the value of D. Oh, currently the value of D is 0 again, so it will set it back to 1. And then do a set context back to thread B. So it will come back here to thread B. So come back to thread B. What's the current value of thread B's D? 0, right? So 0 equals 1? No. So it's going to skip over that. Come back up here, check I is 3 less than 3. No. So it will come here, finish, exit, and then you can just assume we're all done. It's done the process. If we don't say it has a UC link or anything like that, so it's all done. So the answer to this question is, we'll see A1, B2, A3, and be done. So questions about how this works? Yeah?
So before the loop finished, when you switch from thread A to thread B, you said D was equal to 0, and then that skipped the if.
Yeah, so when we came back here, D was equal to 0, right? So 0 does not equal 1, so we'd skip the if.
But I thought it doesn't like save the stack. Earlier you said like it only saved the registers.
Yeah, so the get context just saves the registers, right? So when we were at B before, right, we created D equals to 1, then we saved the registers, then we changed the value from a 1 to a 0, and we set context to A, and then we came back. So when we came back, D was still 0. So that's the value saved on that stack. And like with thread A, the register that got restored is the stack pointer, which would just be pointing at the top of the stack. It doesn't move or anything like that, right? So if I declared D, after the get context or something like that, if I had int A, then it would be recreating that A every time because it would be restoring the state before I created A. So my stack pointer would be before it created A, so when it creates A, it would just increase the stack pointer again and just recreate the same variable over and over again.
Earlier when you switched from thread B to thread A to simulate the context switching, your D was, I think, 1 at the time in thread B. And then when you switched to thread A, your D didn't correspond to, I think, 0, which was what thread A's stack had at the time. It's kind of like hard because you cross some stuff out.
So if I rewind a bit, so here, let's go through fast. So if I rewind, if I rewind all the way, right, I have two stacks. I have two stacks. Initially, they're both empty. Let's just rewind all the way. So UA would start there. UB would start here. Let's see if I can do it cleaner. All right, back to the start, right? So if we start executing, it says we do a set context to UA. So we would start executing. Actually, let's write the code. Like, I'll do arrows this way. So we start executing this line, right? So this would create a variable called D on thread A's stack. So we have a variable called D. Its current value is 0, and it is on thread 1 stack, right? So the stack pointer would be pointing to like the top of the stack like that, right? And these are the values on the stack. So everything here is in memory, and that stack pointer is the register. So we do that. We would go into here, increase that global variable. Who cares what it is for now? Let's just concentrate on D. So this would change D, the value of D on its stack from 0 to 0, so it doesn't do anything. Then we do a get context such that if we restore UA, we would restore the program counter such that it looks like it returns from that function and the stack pointer wherever D exists, right? So basically it's not going to change that stack pointer because we don't declare any new variables or anything like that afterwards. So what it's going to do here is check the current value of D on thread A's stack, because thread A is executing this. Its current value is 0, so this is true. So D equal 1, it will change the value of D on thread 1 stack from a 0 to a 1, right? Then we do a set context to UB. So we start executing UB. This would declare a variable called D. This D is a different D that lives on thread 2 stack, right? So we'll fast forward. Let's just fast forward and assume we did the set context call. So if we did the set context call, we come back here, and that stack pointer doesn't change. We didn't modify it since the last time we saved it, so it stays the same. And the values don't get modified in memory from that get context or setting context back to it. right? It's only the registers that change for that. So the current value of D is still 1. It's whatever we left it, because we're back in thread 1 now, so it's the value of D's thread 1, or thread A. So now if we check, the current value of D is equal to 1, which is not 0, right? So it's going to skip this. So does that answer that? Yeah. So, yeah, when you get context back, right, you have to remember whose stack you're using. So like I just created a stack for thread A. Maybe I should have called that, instead of thread 1, thread A stack. You can assume that every thread would have its own unique stack. All right. All right. Any other questions for that? That's a fun one. All right. So I assumed most people would not, I assumed this lecture would be, reading week. People are still on that. You probably have other midterms based off your schedule. So we can do a fun form of IPC that's not testable, but you can, wreak havoc with this and use the internet. So after this, you can create your own web server, implement your own browser, cause havoc. So sockets are another form of IPC. Aside from setting them up, this is how we do networking and everything like that, and basically how a web server. So we've seen pipes and signals, talked about shared memory. So sockets are just another form of IPC, except it's all on a different physical machine. So what we saw before, pipes, signals, and shared memory, those are processes on the same machine. If you're using a web browser, technically, if I go to google.com or whatever other website, that's technically IPC, but it's a process running on a different machine, on Google's servers, right? But still, at the end of the day, IPC. So sockets enable IPC between physical machines, and typically it's always done over a network. In the little example we have today, I'll show you, I won't be using the network, but you can easily change it to use the network and figure out Google's IP address and all that fun stuff. So for web servers and things like that, there's two things. You need a server and a client. So a server is a thing listening for you to connect to, giving you a response back, basically at the end of the day. So if you are implementing a server, any web server you've ever been to has to implement these 4 steps to use sockets. Again, no matter what language they are written in, because these are all the system calls we have to use. But thankfully for us, they have usual C wrappers. And if you're using Python or JavaScript or whatever the hell, at the end of the day, you'll be using these. So setting up a socket is a bit more involved. It takes 4 steps. But again, I'll just show you how to do that. You'll look it up or look at the lecture or do whatever. So you'll have to first create a socket, then you have to bind. So you have to attach that socket to some location, a file, an IP address, or a port, which is how anything on the internet will work. And then you listen to indicate you are accepting connections and set a queue limit, so how many connections I want to hold in line until I start dropping connections. And then you can do this accept system call, which returns the next incoming connection for you to handle. And if you are the client, this would be, if you're implementing a web browser, this is what it would have to do. It's the client. Google.com has a server. Your web browser is basically a client. If you're using a socket, you're using these 2 steps. You create a socket, and then you do a connect system call, which connects to some location. And then the socket can now send and receive data. So if you want to test out U of T's network, you can connect to any of their random IPs, send it random data, and see what happens and see what you get back if you want to be fun. So how that socket system call works is it sets the protocol and type of socket. So this is kind of, a bit of a preview for your networking course. If you are interested in networking, you'll be using sockets. So domain, it takes 3 arguments, domain, type, and protocol. Basically, that protocol is never used. The domain, in general, that's like kind of the general protocol. So it usually has 3 common options. AF_Unix for local communication on that same physical machine, where the locations we'll see given by a file. Then there's IF_INET, which is an IPv4 protocol using your network. So that'll be an IP address like 8.8.8.8, valid IP address. So you'd use INET, and then IP, or INET6 is IPv6. So IPv4 is what, 32 bits, IPv6 is 64 bits, because we are running out of IPv4 addresses because everyone has connected their toaster to the internet, which of course is a great idea. So we had to increase it. Some things still don't use IPv6, but that just has more addresses. And that type is usually one of two options, stream or datagram sockets, which you might know from as more common names. So stream sockets use something called TCP. Again, I won't go into it too much, but that's for your networking course to do. But what TCP is it enforces some other rules that all data behaves as you would kind of expect, that all data sent by the client appears on the same order on the server, which in general is not true once you deal with networking. Or if I send some, even if I send some information, to your laptop from my laptop over the internet, if the internet works properly, we have a more or less direct connection. If it works improperly, some of the information might get routed through, I don't know, Montreal or something like that, in which case some information is going to appear on your machine before other. But TCP actually behaves as you expect. Everything's shown in the same order, and there's a persistent connection between the client and server. It's reliable, but may be slow. Anytime you connect to a web server, it uses TCP in general. Datagram sockets use something called UDP, so it just sends messages between the client and the server. There's no persistent connection between the client and the server, so you don't know when someone disconnects from you. And it's going to be fast, but the messages might be reordered. They might appear in any order. They might not make it there at all, and there's no way to tell. So typically, you only use this if resending that information would be too slow, like for video streaming. Maybe you don't, if you're doing some live real-time thing, if you miss it, too bad, you just skip a frame and just carry on with life. If you need things to be in a consistent order, you can implement your own stuff on top of UDP, but basically if you want it to be in a set order, just use TCP and don't try and re-implement it yourself. Or, if you take the networking class and you think you can do better, then you can go ahead and re-implement it if you want. So the next step is that bind system call. It takes 3 arguments and it's C, so it looks a bit ugly. So that socket system call always returns you a new file descriptor. So you do bind, you give it the file descriptor you got back from that socket system call. And then because it's C, you have to give it the pointer to the sock address structure and tell it how many bytes long that structure is. So there's a few types of different structures that you can use depending on the type of socket. So there's struct sock _un. I don't know why they shortened it to this degree, but that's short for Unix. So if that's for local communication, it's going to appear as a file. That's what I'll use in this example. Socket address _in is for INET. Again, I don't know why they shortened it to 2 characters, but that would be like an IPv4 address, like 8.8.8, whatever ones U of T owns. And for infix or in6 or IPv6, the IP addresses look like this. They're a bit larger, and they are just written out in hex with a whole bunch of colons to separate out all of the different numbers. So that listen system call sets queue limits for incoming connection. You give it this int socket and then a backlog of how many connections you want to sit there waiting for you to accept them before it starts dropping them. So you can set that limit you want if you want, but we'll just set it to 0, and that just tells the kernel to use its defaults. Usually, unless you have a good reason to, the kernel developers are probably smarter than all of us, so just use their defaults. Then we do the accept system call, so that will block until someone has connected to us. So it takes as an argument that socket. Optionally, it takes another socket address if we want. So that socket is still the file descriptor returned from that socket system call. It should be bound to something and be listening. And then these are addresses if we want to actually just optionally make sure to listen to a specific address, but if we bound to it, we don't have to worry about them. We can set them both to null to ignore them. And what this will do is return you a new file descriptor that represents that new connection. So you are connected to a client, and then you can read and write to it, as we all know and love as usual, because at the end of the day, it's just a file descriptor. All right, so the connect system call is what the client does to connect to an address. Again, it takes a socket file descriptor and an address, so it kind of combines the bind all in one. So that socket FD is the file descriptor returned from that socket system call. Has to be using the same protocol and type as a server in order to connect properly and work. And the addresses are the address to connect to exactly like bind. So you're actually connecting to that server that has been bound to that. So the only difference with this one is if this call succeeds, then the socket file descriptor is now valid, and I can just send and receive data to it using read and write if I want. So we can go ahead and look at the example. So in this example, I have created, this is like a very scuffed web server. So what I do is I'm going to use a Unix socket, and how you connect to it is the socket just looks like a normal file. I'm going to call it example.sock, and this will be created in the current directory. Create a file descriptor, just a global file descriptor, so I can go ahead and close it, clean up my socket and everything like that. Here I unlink socket path, so unlink will get rid of that path name. Otherwise, my socket will not actually resolve to anything. So that's how I get rid of that entry in my directory. And then here, let's go to main. So in main, I register 2 signals because I'm going to have to use signals to go ahead and exit gracefully, because my web server is just going to be an infinite loop, and all the web servers running on the internet are essentially implemented the same way, just a little bit fancier. But all the steps will basically be the same. So here I create a socket, type AF Unix, a stream, so the reliable protocol, check for errors, and then here I set up this socket address for Unix. I have to set the Sun family. Again, this company created this in the 70s, so we have to use this name now, even though I'm pretty sure Sun Microsystems doesn't even exist anymore. So we have to set this, tells you the protocol name, you have to set to AF Unix so it can figure out what structure this actually is. And then here it has this Sun path, so that is to copy in the actual string to that array in that structure. So I can just use stir and copy to go ahead and copy that string into it. And then here I bind to that address, so I bind to that file name, check for errors, listen to it to tell the kernel, hey, I'm actually listening for connections now. And then this is our web server. This is how every single web server on the planet will be implemented. While true, except. So it will sit here at except. It's a blocking system call. So it uses that FD we got back from the socket system call. I don't have to give it any addresses or anything. This will block until someone connects to my server, in which case it will return a new file descriptor representing that connection. So here I can check that there's no errors. And then I'm just going to do, obviously if this was a real web server, it would send you HTML and JavaScript and a whole bunch of other garbage. But for mine, I'm just going to send the string hello there. So I'm just going to do the write system call to that connection, FD, send it the string hello there, and then check if there's errors. Make sure I write everything, and then I just close it when I'm done with it. So I just accept the connection, write out some response, close the connection, and then this will go ahead and block again, while true, until I press Control-C, in which case when I press Control-C or send it the nice term signal, because I registered a signal, it's going to come here, call this close socket function, where it's just going to clean up that file descriptor, remove its name, and clean itself up. And then in the client, all I do, again, create a socket, connect to that same path exactly like on the server, but instead of the bind, the listen, and the accept, I just do connect to it. So I connect to it, check for errors, and then if I connect successfully, that file descriptor now represents a valid connection, where now if I read from it, I read whatever that process has written to it. So I just keep reading all the data we can, just like cat, and I print out all the data we receive, and then just close that file descriptor. So now, if I run this, I can see in this directory, I don't have that example.sock or anything like that. But now, if I run the server, right, it's in an infinite loop. Right now, if I was to strace it, I would see it's blocked on that accept system call because no one has connected to my poor web server right now. It's just sitting waiting for connections. So if I open another tab and go to lecture 12, and I look at the directory, I can see, hey, there's something that looks like a file there called example.sock. It's in that pretty magenta color. Look at that. Look at that color naming. Aren't I fancy? So it's in that special color. It has a weird equal sign. If you look at it, you'll see that it doesn't represent an actual real file. It has size of 0, and it has the special S, which signifies it's a socket. So it's just kind of a placeholder that the kernel knows if you try and access that, it actually represents a socket. So if I run my client now, I can see that my client just receives hello there. So this would be like your web server, or sorry, your web browser. You connect to google.com, which is running in this tab here. Go ahead, connect to it, get data from it, receive, and I can go ahead and connect a bunch of things to it over and over and over again. Hello there, hello there, hello there. I can connect as many as I want. Cool, huh? It's basically a web server. Go implement google.com. This is your first step. All right, any questions about that? Kind of fun, huh? For a definition of fun. All right, so what I can do, I can play with it a little bit if I want. If I control C, it should clean it up successfully. So if I ls here, the server is no longer running. So I see that my example.sock doesn't exist because that closefd actually cleaned it all up and everything. Now if I try and run my client here, I should get an error when I connect that says no such file directory. It doesn't exist anymore. And I can see a whole bunch of different errors if I want. So in the server, if I didn't clean it up correctly, and let's say I forgot to do this unlink, so unlink will get rid of that path.sock name. So if I don't include that, and I compile, I run my server, and then I kill my server, I'll see that I do actually, I'll see that I do actually have this example.sock here, but the server is not running, so it's actually not listing if someone tries to connect to it. So if I go over to my client and try and run my client, now I get a different error from connect. I get connection refused. So it exists, but nothing's there is listing to that connection. And that's probably an error you've actually seen when you've tried to connect to a web server, right? Connection refused. Well, that's why, because it wasn't actually listing for anything. That's why it got connection refused. So any other questions or any other fun things you want me to do with this? So this is your networking course. This is how web servers work. If you want to play around with stuff or try and automate stuff, you can use better languages than C to do this. But at the end of the day, this is what's going to happen over the hood or under the hood. If you're using anything over a network, it will use a socket, and it will boil down to these system calls. So any questions or anything at all? Went faster than I thought. Sure. All right, so let's wrap up, and then we can leave early. Again, I assume that everyone would still be in reading week mode, so I'm not too worried about ending fairly early. So you can perform networking through sockets. It's just IPC across physical machines. Basics are They require an address, local or IPv4 or v6 address. 2 types of sockets, stream and datagram. One's reliable in order, the other just sends it and hopes for the best. If you're a server, you need to bind to an address, listen to it, and accept connections. Each accept call corresponds to 1 connection. If you're a client, you just need to connect to an address. If you successfully connect to it, you can send data back and forth to a server if you want. Again, backbone of how all the internet works. So I will wrap up with that. I will just chill here until 3 if there's any other questions or anything like that. So just remember,